Okay, so welcome everybody for joining this week's seminar. Um, Today we have with us Salmoli Ghosh, which unfortunately, if you guys remember, she was planning on being with us in person in September, but that was possible. So we're at least very happy that you are still giving us a seminar remotely, and hopefully in the future we can make the on-site visit happen as well. So Salman is a four-year PhD student at the National Center for Radio Astrophysics in India. He's working with Professor Priti Garg, which I'm sure a lot of people know around on a very sort of, I would say, not intuitive topic of exploring radio emission of radio quiet sources and specifically Seyferts and Liner galaxies. And she has extensive experience with all different single dish and VLBI arrays, focusing on the multi-scale, multi-frequency radio polarimetric study of large samples of these sources. So today she's going to tell us about polarized outflows in radio quiet AGN. Amoli, we're very happy to have you, and please take it away.
Yeah, thanks, Yanis. Thanks for the nice introduction. Uh, yeah, I'm glad to give this talk. To the online participants, of course, you can feel free to ask me questions in between if something really, is not probably understandable. So just feel free to stop me and ask. Okay, so I'll begin. I'm Salmoli Ghosh, as Yanis mentioned, from National Center for Radio Astrophysics. I'm working on outflows, different kinds of outflows actually, from radio quiet agent, and I'm working with this lovely bunch of people who are mentioned over here mm, very closely. So if you see this image on the left on my title slide, this is an artist's impression of how outflows look like from an agent, and it looks fascinating, right? And on the right side is an image from a real galaxy, which is NGC 3079, and I'll be discussing about it in later on in my slides. I would like to ask you that I think what do you imagine whenever you hear about active galactic nuclei in your mind? Like, what's the usual picture that comes to your mind? I am guessing it's like, okay, yeah. I'm guessing it looks like this for sure, with such energetic jets coming out, and the jets are shown in red, which dominates in radio because of its synchrotron radiation. And the host galaxy, which harbors this region at the center, is shown with the yellow light, which is an optical over here. But unfortunately, if you look for a population of agent, the agent do not look such great. They usually look very boring, and like you can see over here in blue light, blue color, the agent has been, the emission from the agent has been shown. And this is the optical host galaxy, the spiral galaxy, which is harboring the agent. The agent is usually confined within the host galaxy, and is much more fainter and sometimes even undetectable by radio telescopes. Now, all this thing, when Kellerman et al. 1999, in 1989, they studied a sample of quasars. They found that there was a bimodality in the distribution of the radio loudness parameter. Now, radio loudness parameter is usually defined by the flux density at 5 gigahertz to the flux density at optical B band. So basically, radio to optical. In the when they studied this, they found a divide at R value of 10, and it was found that only 20% of the sources have some R value greater than 10, whereas 80% of the sources have a very small R value. Um, Now, these were named, these sources, these 80% of the sources were called as radio quiet source, and 20% of the sources having higher R values were called radio loud sources. But now there are some other definitions of radio quiet sources, like the radio luminosity, like only the radio has to be very small, less than 20, 10 to the power 23 watts per hertz. And to be very honest, the sources that I'm studying, they have a very low radioluminosity. Like this is a plot of radioluminosity at 1.4 gigahertz with respect to the extents of this radio extents of these sources. And I'm mostly, so the radio quiet sources are quite below, and I'm mostly focusing on liners and Seyferts, as you can see over here, which are kind of nearby radio quiet sources. They are at lower redshift radio quiet sources. Mm, Although they are like their radioluminosity is very small, of the sources, they can still extend to a few kiloparsecs, like tens of kiloparsecs. And nowadays there are many more papers where they are even finding 100 kiloparsec jet for a radio quiet source. Um, one thing you need to remember is the black hole mass is found to be usually lower compared to the radio loud sources. Like it usually ranges from 10 to the power 6 to 10 to the power 8 solar masses. And even the accretion rate, it's quite small. For the liners, it's way too small. But for the Seyferts, it can till extend to 1. Um, these sources, these seaports and liners, they usually are low luminosity sources and hence are relatively inefficient. Um, there's outflows. But the thing is, it's not that they do not have jets. People are finding jets. And not only they are finding jets, there have been studies by our groups very recently where they are even finding superluminal motion in jets, that is, the apparent speed exceeds the speed of light. Now you can see the optical host galaxy over here, which is interacting with another galaxy, which is a companion over here. And this contours show the radio image of the source. But when we looked at with the VLBI for the source, it showed an extension along this region, and this blob actually was found to move, like different epoch of data was taken, and this blob was found to move at a speed greater than the speed of light. And these are usually seen in other fast sources, fast jets like lasers and all, but not in case of radio quad sources, and this was fantastic. And there have been also other papers recently about feedback mechanism that they are finding, that the weak jets are kind of driving away gas and all. This paper was on based on the study of molecular gases, and they also find ring-like NUV and FUV structure where there was some like vacancy of star formation at the center, which was inferred due to the weak jet activity over here, for two NGC 2639. Now, with all these ideas, still there are like these studies have been very recent, and still there are a lot to explore in the radio quiet regime. Like there have been a very good review by Panessa et al. In 2019, which discusses about the different origins of radio emission in a radio quiet agent. I think it's a good review to go back and see. And the most important question is why and how these are different from the radio loud sources, and what's driving the outflows over here, whether it's magnetically driven or some gas pressure is there or radiation pressure is there, which is the most dominant thing, which is making this outflows to even exist till a few kiloparsecs. And what's like how are they impacting the host galaxies? All these things are still like unknown to the community, and people are trying to approach it with different things like multi-wavelength studies. I'm pretty sure many of them are doing with the x-rays and even optical, and I'm currently focusing on the radio polarization study of it to understand what's happening in the sources. Now, we have actually selected 26 such radio quiet sources. The sample is small, but like we had some selection criteria based on which the sample became so small. We took it from a complete sample of Seifert and liners, that is the extended 12 micron sample and Center for Astrophysics sample, compiled by Gallimore et al. 2006, when they observed it with the VLA. And they found like almost half of the sources show kiloparsec scale radio structure, or which we call as quasars. And there were many point sources which didn't show any extended radio feature. We actually kind of ignored those sources whose radio emission closely aligned with the optical host galaxies, because it has been suggested that in those cases, mostly those radio emissions contributed by the stars in the galactic arms, or in the galaxy, basically. So we ignored those sources. And this extended radio emission actually kind of helps us to study the sources spatially. Um, Now, this is a glimpse of the sources that we published in this paper, and this you can scan this to get the to get I mean to get to the paper. Um, what happened is, because of a selection criteria, we could actually rule out the coronal origin and the stellar origin as well for the radio emission in the sources. And all the sources, as you can see, were detected in polarization. So this red ticks that you are seeing now, these are electric vectors, or the polarization vectors, and their lengths are proportional to the fractional polarization. So all these sources are heavily polarized, as you can see. Um, and yeah, so these are all the sources, but I'll also show you some different kinds of sources that we found in our sample. So a few of the sources had Asian contribution along with stellar contribution, because you see the colored images show the optical host galaxy, and some of them have aligned radio emission along the disk of the host galaxy. But there are also some radio emission perpendicular to the direction of the host galaxy. That is, or maybe we can say the emission along the minor axis of the host galaxies, which we are really concerned with. We think those are from the AGN. Um, so this kind of sources are very difficult to study, because it's difficult to disentangle the stellar contribution and the agent contribution. And then there were sources which were much more cleaner and only had agent contribution. And then there were sources which were termed as point sources in Gallimore 2006 paper. But we were finding some extended radio emission with our more sensitive and highly resolved, higher resolution telescopes. And okay, so I think not all of you are familiar with polarization, but why we kind of focused on polarization is that because with the help of polarization, we can get to know the direction of projected magnetic field lines. And how is that? By rotating the polarization vectors by 90 degrees, if the emission is optically thin. So that you have to keep in mind, when the emission is optically thin, then by rotating the EVPS by 90 degrees, we get the magnetic field directions. Um, and like if we get to see a higher polarization fraction, then of course the thing has to be that the orderness of magnetic fields are more. And that is possible only if there is some presence of agent-like source which kind of drives ordered magnetic fields along their emission. And also the magnetic field orientation, the direction of the magnetic fields, they help us to understand how the jets are being launched. And the magnetic field geometry, like whether it's tangled or helical, they help us to understand which of the proposed mechanisms, like Blandford-Snag, Blandford-Payne mechanism, which is the most favored one in these cases. And also there's something called rotation measure, which basically gives us the angle between the intrinsic polarization angle and the observed polarization angle. And that change in polarization angle of polarization basically gives us the idea of the intrinsic medium intervening medium, which is kind of rotating the vectors. So with the rotation measure, we can get some idea about the jet propagation and the intervening medium, which is interacting with the jet and probably doing something to the polarization vectors. I mean, the polarization of the sources. Now, I just before getting to the results, I'll just say that we use a data reduction procedure. I mean, we follow a data reduction procedure for our radio polarization data, and we use CASA, Common Astronomical Software Application, for reducing the data. We get the UV data, and then we kind of delete or remove all the bad data which usually gives a lot of higher values and all. We remove them and then we calibrate using a model. I am just quickly going through the slide because if anyone is interested, just let me know. We can discuss later. But this is what we follow. Then we calibrate and we apply the calibration. Um, but afterwards, we recalibrate again, again removing the bad data, and this procedure continues until and unless the calibration converges. And then what we do is a polarization calibration, which is an extra step for us. Um, and after the polarization calibration is done, we apply the calibration and image it, and we image the full Stokes thing. So for our observations, radio observations, we need extra polarization calibrators, and we need to observe it in a full Stokes mode as well, so that we get all this information afterwards. And when we got the Stokes IQUV values, we get the polarization angle by using this formula, the polarization fraction by using this formula, like with the Stokes Q and U, and the circular polarization is given by Stokes V. And if anyone wants, you can scan this QR to get to my GitHub page where all the polarization pipelines are given for we have a pipeline for VLA data reduction as well as for GMRT data reduction. If you know, these are two very well known radio telescopes, interferometers. Mm, yeah, which we are using on a daily basis to get our data and reduce it and get this images basically. So, for today, I would like to highlight some of the results from the 12 sources that we got from our VLA study. The study is still continuing. We are still getting some data, and the paper is also still in preparation for the rest of the sources. So this is the redshift distribution, and if you see, these are all famous NGC sources which have been studied again and again with in optical and X-rays as well. We are doing the radio study with the polarization polarimetric tool as well. So these are all nearby sources, and the radio luminosities are also very low, as you can see from here. What we found for the complete sample is most of the sources do follow a correlation with the black hole mass, like all the radio properties like radio loudness parameter, the core radio luminosity, the total energy, and even the jet kinetic power. That also strongly correlates with the black hole mass compared to the accretion rate. So we kind of deconvolve the interdependence between the black hole mass and the accretion rate. And then we tried doing this partial correlation, and we found that black hole mass is kind of coming out to be a stronger factor in case of this KSRs, or the kiloparsec scale structures, the extended radio structures from radio quiet agent. So that is a great thing, I would say, because this has been found for radio loud sources. Um, but for radio quiet sources, people have studied similar things, but this has not been found before. Um, Now, we also try to see how the polarization fraction is dependent on the accretion rate. So over here, we took Eddington ratio, which can be considered as a proxy for accretion rate. And what we found is when we looked at the core of this sources, so core is basically the unresolved part of the jet, which is at the center. So what we found is the fractional polarization to actually anti-correlate with the Eddington ratio. And this says that when the accretion rate is higher, there are more material near the core, which is actually depolarizing the source, decreasing the orderedness of magnetic fields in the source. Whereas when we went to the extended lobes, what we found is a correlation. So that is the thing, like with higher accretion rate, the fractional polarization was found to increase. Now that says that when there are more material, when there's stronger accretion, the outflow becomes the extended outflow becomes more stronger and more jet dominated. This is also something helpful for us to understand these sources, how their jets are being launched, and how they are correlated with the accretion rate. Now, I would like to focus on a few specific objects, like, say, for example, NGC 2992, and would like to actually, I would show many more objects and show what the important result we derive from them in terms of being a radio quiet agent. So, this is one source, and this is 2992, which where we could see in the VLBI, the jet has one, like there's a small extension over here which says the jet is in this direction, but the VLA feature shows a small H-shaped structure over here. And with the VLA 10 gigahertz survey by us at 7 arc second resolution, we couldn't really resolve any of the structures. We just found a blob-like feature over here. um, but the interesting thing is, in the each alpha map, it shows another limb over here, which is outside the VLA ARA feature, H-shaped feature, which is shown with in the black. Um, Now, with our polarization study, we also found a higher polarization fraction. And as I mentioned, the ticks are proportional to polarization fraction. So we found a higher polarization fraction region over here, which kind of coincides with this extra limb of H alpha. And Arvin et al., they found a relic emission in this region. So that says that this newly emitting jet is probably compressing a region over there, which was previously a relic, but now it's being re-energized by this jet, probably increasing the polarization fraction over there because of the compression of the magnetic fields in this region. And yeah, so and this jet is kind of uh, feeding to the galaxy probably. So it's like a positive feedback happening in this region of higher polarization fraction. Um, Now I would like to show you another galaxy, which is NGC 3079. And like as I mentioned, it has a radio emission along the galactic disk. Like in the H alpha map, you can see also the galactic disk is along this. But what we are concerned with is the emission perpendicular to the galactic disk emission. Now you can immediately see that the emission which is perpendicular has a higher polarization fraction. And this is actually what it's thought to be coming out from the AGN, this lobes. Um, what happens is, as you can see over here, there is a strong Asian activity happening along this region. But if you look at the H1 map, there is a scarcity of H1 along this radio emission from the Asian. Now, this is the thing that if the strong Asian activity is making the galaxy devoid of its reservoir of neutral hydrogen, which is required for star formation activity at the central part of the galaxy, then it's acting as a negative feedback for the galaxy, at least for the central part. Although it's not affecting the rest of the galaxy, but it's definitely affecting the nearby region, which is the central part of the galaxy, and is reducing the H1 amount quantity in this region. And this is another galaxy which is called NGC 3516, which I'll come back in greater detail. Um, I'll come back to it. These are the radio contours shown over here. And as you can see, this is the spectral index image. If you're aware of like basically how the flux is changing over frequency, this reflects that. And older episodes show a steeper spectral index, whereas a re-energized or a newer episode shows a flatter spectral index because of their being currently fed by something. Okay, so that's the thing, that the spectral index map also shows a jet-like feature over here. And then there is a region of flatter spectra, which is most probably a hotspot or a shocked region in this case. But this radio quiet source even actually imitates a radio loud source, mostly the FR2 sources, where there is a jet and a edge hotspot. And if we look at the polarization vectors, so as I mentioned, the magnetic field vectors will be perpendicular to this source, perpendicular to this electric field vectors or the polarization vectors in optically thin regime, thin emission. So we can consider the magnetic fields to be along this jet-like emission and becomes perpendicular at the edge, at the shocked front. Um, so this is exactly like the polarization features observed in an FR2 source, where the magnetic fields are along the jet and becomes perpendicular at the edge where the shock front is. Now, I would also again go back to the Gallimore et al. 2006 paper, where they claimed that some of the sources didn't show any extended features because, of course, of their resolution of they had a resolution of 15 to 20 arc seconds. So they didn't see anything. They just saw a point radio source, which is marked by a plus over here. But interestingly, what we are seeing with our VLA BRA 3 gigahertz observations is an extended structure in the radio. And it's very interesting um, that although some sources may look like a blob in radio, if we go to the correct resolution, correct frequency, correct sensitivity, we may pick up something, and we may pick up proper collimated jets. Even if we go to a much higher resolution, but we also need to have the sensitivity. And interesting thing is, we are also finding a lot of polarization at the center. That means it has some polarizing agent, which is most probably a jet inside it. There's another source which was again found to be a point source in the paper, in the Gallimore 2006 paper, but we are finding a double lobe kind of structure with one of the lobes being polarized, which is probably coming towards us. The other lobe is not so polarized. I mean, it's almost depolarized because probably there are more materials in front of this lobe and it's a receding lobe. Now, I'll also come back to that 3516 source. And as you can see that the radio loudness wise, it's quite small. And if you also see the radio flux densities, it's way too small for proper detection. The extension is about 10 kiloparsec, which is a good thing for us because we can then see the sources very well. The jet power is also on the lower side. Um, when we looked at that source with higher resolution, what we saw is the northern lobe only. The southern part of it is below, it should be below, but we couldn't detect any of it. But the interesting thing we detected is the core, and then there is a small jet knot above, which says that there is a strong jet over here. And the jet knot actually continues and ends at an H shock over here. Um, Another thing which we found is the jet bifurcates in this region, and this source have been studied with optical quite a lot because it has a very well-known S-shaped morphology of the O3 and the H-alpha emission. And now, when we studied this parallelly, you can look at the paper also by scanning this QR. When we looked at it, we found that the bending of the O3 and the H alpha is happening exactly at this bifurcated region, and that says that but the radio jet still continues, by the way. So that says that probably that bifurcation which is happening is due to the jet itself. The bifurcation that is happening in the optical is mostly due to the jet. So maybe the jet is entraining mm, the NLR gas or something, and it's kind of bending it along this region. Because of precision, maybe we also fitted a precision model, which I have not shown here. Um, and we find the core to be highly polarized. And the interesting thing is the core has magnetic fields. So these are again polarization vectors. So the magnetic fields are um, perpendicular to this, so also perpendicular to this outflow direction. So these are called toroidal fields because yeah, it's interpreted as these perpendicular fields are interpreted as toroidal fields, and the toroidal fields actually helps to give rise to wind-like feature. And we also did a rotation measure thing with the rotation measure estimate with the different polarization data that we had. As I already mentioned, rotation measure is basically the rotation measure multiplied with the wavelength square actually gives the difference between polarization angles of the observed one and the intrinsic one. Now we got a rotation measure map from there, and what we found is along the transverse direction to the jet outflow, there was a gradient. The gradients have been shown over here. So we are now only concerned with the blue and the red slopes, which have been shown with the blue and red. Because these are the transverse gradients. And if you see what Rm depends on is basically the electron density Me, the magnetic field, the line of sight magnetic field, basically, and the length of the Faraday rotating medium. Now, these two factors won't change the direction won't change the sign of Rm. But if we see Rm to change from negative to positive, of course, it has to change its sign because of the change in direction of the magnetic field lines. So, this is how it's interpreted is that when the rotation measure increases from this to this, then it has to have a helical magnetic field. That is, if it's positive over here in the red region, then the magnetic field is coming up in this region, and if it's negative in the green region, the magnetic field is going down. I mean, going into the board, plane of board, you can say. So that's how a ring is being formed, and that's how a helix is being formed. And this kind of fashion, no, where the gradient goes in opposite direction, they say that if the same engine has to same central engine has to produce helix in opposite directions in it along its two lobes, then the gradient needs to be in opposite direction, like shown over here. Um, so this is exactly what we are finding for our radio quartz source. Now, these kind of rotation measure gradients have been studied by K. Asada and Gavuzda for radio loud sources, and they have been claiming similar things that probably these are being powered by helical magnetic fields. These jets are being powered by helical magnetic fields. But no one has done a similar study, or maybe, I mean, no one has done much study with polarization with the radio quiet sources, because of course they are faint, and in polarization they become fainter. Um, so this says something that these radio quiet sources are not much different from the radio loud ones actually. But only there are other things which I'll be discussing, which differ from the radio loud sources, but not at least in the jet mechanism procedure or jet launching procedure. Um, and what's interesting is that this is the X-ray image of the source, but like no one has found an X-ray jet in a radio quiet source before also. But we are finding an X-ray jet over here along the radio jet. And then there is a diffuse X-ray emission as well, which doesn't I mean, it doesn't appear well in this image, but there's a diffuse X-ray emission that we can see, and we try to fit those X-ray components using chow and expect, and we could fit three wind components in this range of NH, like the column density. Um, and that says that there is some ionized wind present in this source along with the X-ray jet. Um, so there's another source, NGC 4151, which also showed some interesting feature in radio polarization. But this is a bit different from the previous source because we can see the radio flux densities are quite higher. So this is on the higher side of radioluminosity compared to the other radio quiet sources. And the extent is extremely small. It's only 1 kiloparsec, but the jet power is also on the higher side. And interestingly, we see a lot of polarization in the source, but all this polarization has different directionalities. At the central part, we see an aligned magnetic field. So these are magnetic field vectors shown over here by rotating the EVPS by 90 degrees. So I've already done the rotation. Now these are magnetic fields. But we see at the central part of the jet, so the jet, even in the VLBI direction, is along this region. So the central part shows an aligned magnetic fields, but there are some extensions, as you can see over here, where the magnetic fields become perpendicular somehow. Um, and this concept was previously explained in this particular paper, Medipura and Constantini 2019, where they said that there's a transition from poloidal, which is aligned magnetic fields, to toroidal fields when the jet converts to wind. So there is a thing of jet domination versus wind domination. But this is how we interpreted that these extra things are probably radio winds, which people have not seen in radio previously. Um, and when we looked very closely, what we found is the wind part remains, but the jet part now gets divided into two parts, where at the central part, the magnetic fields are perpendicular to the jet direction, and at the edges, the magnetic fields become aligned. So this is something which have been seen in a spine sheet structure or a velocity gradient that is found in FR1s, which are radio loud sources again, where the magnetic fields are usually perpendicular at the central region where there are multiple shocks, but becomes aligned because of shearing due to the interaction with the medium. Now, this thing have been previously, like as I was mentioning, this particular paper, Mehedipur and Constantini, they have actually made this plot where they have showed that radio loudness parameter is anti-correlated with the wind, the ionized wind column density. So their claim was that when the jet is stronger, as you can see over here, the radio loudness parameter is higher, the winds are less strong but less in density. But when we go to lower radio loudness, where the radio loudness parameters are about 10 and gets into the radio quiet region, the winds become stronger. And we find a similar trend for NGC 4151 as well. So this is what made us conclude that probably, okay, let me go back. So that probably this thing continues and even continues for the radio quiet sources, because their experiment was only on the radio loud sources. But we think that this extends to the radio quiet regime as well. And for the radio quiet sources, the winds become even more powerful compared to the jets. Now, the thing is, what are these winds? Basically, we are talking about what are they driven by? So, winds, in order to flow, they either need to be pressure dominated, thermal pressure dominated, or magnetically dominated, or radiationally dominated. So, what is happening in for the winds that we are seeing in radio? So we calculated the magnetization parameter, which is basically the ratio of magnetic pressure to thermal pressure. And we find that the magnetic pressure is dominating for our source. So that means that these winds that we are seeing, they are actually MHD winds, other magnetically driven winds. Um, and we also calculated the kinetic energy of these winds. But the kinetic energy is kind of on the lower side, and it was found to be about 0.01% of the bolometric luminosity. So that says that these winds are very, they are feeble. They are magnetically dominated, but they are feeble. So they cannot actually cause any galaxy scale feedback, but they can affect their immediate local regions and alter the star formation or stellar activities in the regions in the vicinity. So the winds are important in that way. This paper we have recently submitted to ABJ. Um, and what
It's
about
5 minutes. It's 5 minutes
yeah,
left.
sure. Thanks. What about like how does this winds look like? So, these winds, like we were saying, no, the extended regions, are maybe winds, and we check the rotation measures in these sources as well, and we find the rotation measure is positive in this region and negative in this region. So maybe what's happening is the magnetic field in the upper northern wind is coming out, and the magnetic field is entering the plane in the southern wind. So it's like a kind of cover, like a shell kind of thing. And the imagination that we have about the winds in a radio quiet source is like this. Like we tried to make a cartoon out of it. So there's this jet with a helical field, but with a smaller pitch angle. But then we have a jet, like a biconical jet, an envelope kind of thing, where there's still some helical magnetic fields present, but with a like larger pitch angle. And the if we take a projection of that, then we get to see this perpendicular magnetic fields in the wind, whereas aligned magnetic fields in the jet. But if you look closely again in the jet region, then at the central part there will be perpendicular magnetic fields because of the shocks, and the aligned magnetic fields, which will be greater in magnitude, they will be there aligned along the outflow due to shearing. Now, this is one of the major results that we find from our radio quiet study of our radio quiet sources, that there are dominant wind like outflow compared to the jet like outflow. And that's why these are different from the radio loud sources, because there the wind like outflow is smaller or less in dominance. Now, we also do, as I mentioned, we also get the RM rotation measures, and we have multiple frequency polarization data. So from there, we also constrain our depolarization models, like how the sources are being depolarized. So the observed polarization fraction actually depends on intrinsic polarization fraction, electron density, line of sight magnetic field, and of course the length scale of fluctuation of the medium, the total length of the Faraday rotating medium, and of course the wavelength. So fitting all this, what we find for the radio quiet sources is that their intrinsic polarization fraction is much lower than compared to a radio loud source where the intrinsic polarization fraction is higher. So intrinsically, these sources are less polarized, but the thing is the fluctuation length scale, which is required for depolarizing these sources, and are much larger compared to what we find in for a radio loud sources. So we studied this radio loud source in this paper. You can follow this up as well. But afterwards, I started studying radio quiet sources, and I found there's a difference between the radio quiets and the radio louds. Um, Similarly, we did a internal depolarization calculation. So, external depolarization is basically when the Faraday rotating medium is between the source and the observer. But internal depolarization is much more complicated. That is when the depolarizing material is mixed with the radioplasma and is kind of randomizing the magnetic field over there. So over there, we get to calculate the randomized component of magnetic field and the uniform component of magnetic field. And also like other things like the mass of the thermal gas which needs to be mixed to get such depolarization results. And there you can see that the mass of thermal gas, which needs to be mixed for radio quiet sources, are much larger in solar masses, sorry, are much smaller in solar masses compared to a radio loud source. So a radio loud source will need at least 10 to the power 9 solar mass of thermal gas to mix with the radioplasma to get it depolarized, whereas they need a smaller thermal gas mass to depolarize these sources. So, with this, I would like to go to my conclusions, where after studying so many radio quiet sources, mainly Seiferts and liners, what I found is the origin of radio emission in these sources are still the agent-driven jets or winds. And their nature is also quite similar to the radio loud ones, as they kind of all the properties kind of correlate with the black hole masses, as I mentioned, which even match with the simulations. But also, we get to see some stratification in magnetic fields, which are usually seen for a radio loud sources, for a radio loud source. But the interesting thing that we find in extra with the radio quiet source is there's a strong presence of wind, which is probably not there much in a radio loud source. So the winds make a lot of difference between the radio quiet and the radio loud source. And in terms of feedback, I showed you some pictures where we have also found, and other people have also found, some hints of positive and negative AGN feedback, where the new jet activity is either enhancing the star formation or making it devoid of the reservoir of star formation by depleting the H1 gas, the neutral hydrogen gas, and all. And also from our study of polarization, we find the plasma conditions, how much things are getting depolarized and by what. depolarization is happening, whether there is some external media that is depolarizing the source, whether the plasma within, which is getting mixed, is depolarizing the source. So all these informations are kind of helpful to understand the jet medium interaction that is happening in a radio quiet region. So that's where I would like to stop. Yeah, thanks for the opportunity, by the way. Yeah, to give this talk.
Thank you very much, Salmoli.
Yeah,
Thanks.
thanks.
A lot of work. I'm sure there will be also probably a lot of questions. Let's see if there is somebody who wants to start. Yes,
Yeah.
Nick, please. Nick, do you have a question?
Nick, you're muted.
Yes. Okay. It was a very nice talk. Thank you. Could you show us the figure where you showed the magnetic field in the spine and in the sheath? Okay. There. That one. The previous one.
Yeah.
No?
This one, right?
No.
Or this?
The schematic.
Okay, schematic.
Next. No.
This one?
No.
This one?
Continue.
No? Okay, wait. No. Okay. I think the spine sheet I showed over there only, right?
Schematic
Here.
where you showed the central part where the magnetic field was going up.
Okay, I see. This
That
one.
there, that one.
Yeah.
So this is the polarization, right?
Right.
This is
No, these are magnetic field lines.
these are
These ones.
magnetic
Yeah.
field. So the horizontals, what do they mean?
So the horizontals mean, so if we consider the outflow direction to be along this direction, along the north-south,
Yes.
then the horizontal means that the projected magnetic field lines are perpendicular to the direction of the outflow. So if the direction of the outflow is like this, the magnetic field lines are perpendicular. And these are being produced because of shocked regions, like shocks in along the outflow. So the magnetic field lines, okay, even this, if I don't know, if I can annotate over here, yeah. So if there are springs like this, maybe helix like this, and if they get compressed, then what happens is if they get very compressed, then we get to see lines like this when the direction is this way. Okay. So then we get some perpendicular fields.
Okay.
But
So the magnetic field in the spine is along the axis, correct?
In the spine is perpendicular to the axis. In the spine, it's perpendicular, considering the direction of outflow to be north south.
Okay, but magnetic field lines are closed. So where do these lines close?
Oh, okay. Yeah, so it's a helix. So it gets close somewhere, like over here. It follows the laws of physics. I mean, these are not open lines. These are like helix and they close properly. Yeah, at the edges. Yeah. Yeah.
And the other lines that are vertical, where do those close?
Yeah, so these are like projected lines. Okay. So these are also helix, which are being stretched. So if the helices are stretched, in projection, they would look like this. So these are not like, these are the lines. These are projected lines of the helix. You can consider these to be a larger helix, which is being stretched. And these lines are kind of in projection. How would they look like? So these are not like actual open lines or something. These are like in projection, it would look like this.
I thought with these observations, you confirmed the so-called cosmic battery that was done by Kontopoulos.
Yeah.
You aware of it?
Sorry, no, we didn't actually get into that theory of cosmic battery.
No,
Yeah, no, we didn't. Sorry.
yeah, it's not a matter of doing theory. It's a matter of
Hmm.
seeing if the theory agrees or disagrees with the observation.
True, true.
Okay.
True. No, yeah, these are
As if
like we.
it looks
Sorry.
as if it disagrees,
Hmm.
uh, because the prediction of the cosmic battery is that the magnetic field will be poloidal, up,
Hmm.
down, and that at the center will be going up, and outside it will come down. Now, this is
Hmm.
not what you're showing. So, uh, at least that magnetic field I understand physically. There is a current,
Hmm.
and that current creates a magnetic field. I don't know what kind of currents create these magnetic fields.
Yeah, actually, okay, again, I would like to say that these are like what geometry we are finding are helices, like helix, which are being either compressed or stretched. And these are again the projected magnetic field lines. So the magnetic fields do not actually look like this, but like this, the one shown on the left. So it's like that. Yeah, but of course, I would like to continue the whatever you have been discussing with the cosmic battery and also the magnetic field line freezing with the plasma, radio plasma. That would be something very interesting because this is completely from an observational point of view what we are seeing. Like as you can see over here, we are seeing the exact same thing which I've represented with the schematic. So something
Okay,
with
thank you.
a yeah, yeah. Thanks.
Okay, thanks. Any more question? Meanwhile, I have one. So in one of your first slide, where you show us this study on a sample of, I think, where Seifert with probably GMRT or VLA data in polarization, and you show us a slide with some correlation between the accretion rate or
Right.
with yes, this one. Yes,
Hmm.
exactly this one. Thanks.
Hmm.
So,
Yep.
so the conclusion of this plot on the left for
Hmm.
you is that higher accretion rate produce a core which is less polarized. The fractional
Right.
polarization is lower, right?
Right. Right.
I have difficulties it's not something that actually I recall happening in radio loud sources. So if it's something
Hmm.
confirmed here, it's an important result also for radio loud, or to see at least if you can extrapolate it in a sample of radio loud
Right.
sources. Um, but I have a bit of difficulty in understanding what is the mechanism behind this.
Yeah.
So if do you suggest
Yeah.
basically that when you have a higher accretion rate, you produce jet, which should be more powerful, but at the same time you have a less ordered magnetic field, so you are dominated more by a turbulent magnetic field? Is this what behind this explanation, or something else that I'm
Yeah.
missing?
So, yeah, how we tried to interpret this result was that when the accretion rate is increasing, then there is like more infall happening, and that infall is actually so deep. So these are the observed polarization fractions. So what is happening is that is kind of depolarizing the source more with higher accretion rate at the core. And that's why we don't see it in the extended regions. We see an opposite trend in the extended region. But at the core, the it's really getting affected by the material that is infalling, which is kind of randomizing the magnetic field over there. Yeah, and that's how we interpret the results.
So for you, the magnetic field then is also associated somehow with this infalling material.
Yeah, I mean, it's kind of randomizing the magnetic field. The intrinsic magnetic field is still there, but it's kind of randomizing it, and that's why lessening the polarization fraction that way.
Okay.
Like intrinsic polarization fraction may still be higher, but what we are observing is maybe going down. Yeah.
So yes, in the sense that you have kind of an in-beam depolarization, right? So you have
Yeah,
kind of
right,
multiple components, if I understand correctly, you have multiple components
exactly.
with different magnetic field.
Exactly,
and this
yeah.
somehow you associated with the material. So for you also, this infalling material somehow is carrying some strong also magnetic field in order to have this
Yeah,
effect, right?
yeah,
Okay.
exactly. Yeah.
Okay, well, something interesting. Did you perform any Faraday rotation analysis in these sources to see also if
Yeah,
what are the
yeah, right.
conditions?
Right, not for like some of the sources, of course, like I showed some of them. Yeah, and yeah, like these are the rotation measure maps, and then I have a few over here only. This was one of the rotation measure map of one of the sources, and we also calculated how it's being depolarized, like which can be the possible source of depolarization. So we find some external depolarizing agent as well as some internal depolarizing agent as well. And we've also calculated the randomization of magnetic field and the uniform component of magnetic field from the depolarization results.
Okay. Okay, thanks.
Yeah.
Okay, any more question? Let me see here the list. I don't see any raised hand. Then I will take advantage and make you only one last question.
Yeah, sure.
So I think it's a couple of slides before in this source where you have a wind and you have also the NH. You estimated this one, yes? I think this one you have also estimated the NH. So how did you get this measure? What are the evidence for you here that you are dealing with a wind? That for me is something like an outflow. Do you see this line like? Do you have something blue shifted? How do you? What is the evidence for
Yeah,
this to claim that is a wind?
Yeah, these basically are from X-ray analysis. But the thing is, we have taken the value of NH from some other paper by Koto et al. So from there, we have taken the whatever they have quoted for a wind component, but probably they have also done a fitting like this, like we did for something, and we also could fit a wind component uh, with that. Like they are also some doing some wind component fitting, probably, and that's how they have derived the NH for wind. I mean, they
So
have. Yeah, sorry.
Sorry about this. I'm not an expert in hearing this exact X-ray observation
Yeah.
where you said you fit the three wind component.
Yeah.
Do these components differ for some for example, infalling material? So can you distinguish? How do you distinguish just from X-ray observation that is an outflow and not an inflow, for example?
Okay, yeah. I understood your question. It's a really good thing. But I'm also not a very expert. What I did was to use some components, some the templates that are being produced by this Chow for Chandra telescope, and they have specific wind templates. So That is how we just fit the spectrum of the source of the wind region. So, first of all, we see some kind of uh, extended structure in the X-rays. And again, we don't like me as an observer, I don't know whether it's an outflow or an inflow, but they have templates for wind regions. And after fitting that spectrum with the wind template, it matches. That's how they know, but I'm also not sure about how they are understanding whether it's an outflow or an inflow. Maybe some, yeah, blue shift, I don't know. Mm, Yeah,
Okay, thanks.
yeah, yeah, thank
Okay,
you. But I would love to interact with you people even more afterwards because, as I mentioned, I am only doing radio polarization right now, that also from an observational point of view. But if someone can give me suggestions about other wavelengths, and yeah, it would be fantastic for
perfect. We
me. I
have
would
your email
appreciate.
because I put you in CC, so
Yeah, sure, sure.
everyone has your email now.
Yeah,
Thanks. Thank you very much again for your talk and for being here
yeah,
today.
thank you. Thank you.
Bye, everyone.